Hello everyone and welcome back. So this time we'll be learning how to calculate the moment of inertia for different shaped bodies. So let's jump right into it. First off, have any of you ever seen a flywheel? Like maybe you haven't seen a flywheel for like this large metal cutter, but you've seen a flywheel of some sort. It's spinning, and if you look at them, what you usually see is that most of the mass of the flywheel is located at the edges. Most of the mass of the flywheel is located at the edges. Now, why is that? What's going on here? Well, that's because that's going to maximize our mass moment of inertia, which we want, because in doing that, it's going to have a lot more rotational energy in this flywheel, which will help it to cut. So when that cutting blade right there hits something, it's going to want to slow down, but all of this inertia right here at the edge that's spinning around, all of this is going to keep that wheel turning and keep that saw blade cutting. Another place you might see this is if you're looking at a crank on the oil pump rig. And if you look right here, you see the crank, and it's got this big counterweight. Now that crank develops a kinetic energy, and it's related to its mass moment of inertia. So as the crank rotates, its kinetic energy is converted to potential energy, and vice versa, which is helping us move this thing up and down again, over and over again, and pumping out that oil. Now, one question for you then is, this is rotating about this axis, but obviously that's not symmetric, and so its centroid is somewhere over here. And so one thing I want to ask you right now is, do you think the mass moment of inertia around its centroid is bigger than the one around this point A, or vice versa? Spoiler, it's bigger around point A. So, if we're looking at this mass moment of inertia, well, what is it coming from? How do we calculate it? So if we have this rigid body, so we're back to blobs. If we have this rigid body, there'll be some axis, Z, and it's going to pass through our centroid. Now if we apply a torque about that Z-axis, the body is going to begin to rotate with an angular acceleration of alpha. Now torque and alpha are related by this equation. So the torque we apply is going to be equal to my mass moment of inertia times my angular acceleration. It's just kind of like your force equals mass times acceleration equation, just now written for rotation instead. So the mass moment of inertia is a property that measures the resistance of the body to angular acceleration, just like your regular mass is the property that measures the resistance to just linear acceleration. So mass moment of inertia is the resistance to angular acceleration. This one is the resistance to, or mass is linear acceleration. So they're kind of connected in that way. Now, if we look at this, how we're going to calculate our mass moment of inertia is not necessarily the easiest thing in the world, especially if it's a blob. With these blobs, it's going to be much more difficult to do. However, there is a nice equation. It's simply r squared times that little element dm, and obviously we're going to have to integrate over the entirety of the mass to figure out what it is. Now, that might seem very difficult to you. You're like, well, what am I going to do? This is a crazy shape, and you're right. But we very, very rarely ever do it in terms of crazy shapes. What we'll do is we'll make a differential element that is something we actually know. So like there's a set form for the mass moment of inertia of a disk or of a rectangle. And so we choose one of those two, say this is the shape I'm going to use for my mass moment of inertia, and then I will integrate with that. So like for this particular setup, I might have a disk. I know what the mass is of the disk. This little element, I know what the radius is of this disk at this point, and then I integrate all the way up or down or sideways, whatever we need to do to get the full picture of the mass moment of inertia. And I promise you we'll do an example of this with an equation, so you'll get to see how it works. So let's go ahead right here. So when you're doing it, there's two ways you can do this. One, you can use disk elements. I know it's the bottom one, but I'm doing it first. Just because I like it better, that's what I usually do if I'm doing myself. And you'll have some radius y, you'll have some thickness dz, and you can figure out what the volume is. So the volume dv will be simply equal to the area of your little disk times its thickness. and then you integrate to solve. You can also use a shell element, which is like a little cylinder right here, and you can keep on expanding outward. In this case, it's going to have a height z, a thickness dy, and a circumference, which will be 2 pi y. And so we set that up, we do our integration, and we solve. So, one last thing to talk about is the parallel axis theorem, because all these things have been saying we're going to spin around our centroid, and that's the term right there. That's the mass moment of inertia if we're calculating it just around our centroid. However, in a lot of cases, we're not. We're not calculating around a centroid. And so what do we do then? Well, then we add on this correction term, which is simply the mass of the body times the perpendicular distance between the parallel axes. So you have some axis that's going through your centroid, you have some axis that you actually want to rotate around, and you have to find that perpendicular distance, okay? It has to be perpendicular. When you find that, all is well. You can go ahead and solve. So you'll calculate your mass moment of inertia with just your equations or integrals first, and then you'll correct that with the parallel axis theorem afterwards. So, I thought I had it there, but there's one last little thing. That's the radius of gyration, which I'll let you read on that on your own because I don't really think it's all that important for what we're doing. But composite bodies is important because the amazing thing about mass moment of inertia is that if you know what the moment of inertia is for, let's say, a square or a cube, I guess, and you know what it is for a sphere, well, guess what? If you have one that's a square and a sphere, then you just have to add the mass moment of inertia of each. So I know what the mass moment of inertia is here. That's I1. This is I2. And the mass moment of inertia for the total product is just adding those two together. You don't have to do anything crazy. So you just take all the simple shapes you can find, you do them all individually, and you're done. It's just like when you're saying, like, I don't know how to take the area of this strange shape, but you know how to take the area of a triangle and two rectangles. You just add them together. So that's it for this time. Thank you for listening, and I'll see you all later. Have a wonderful day.